Chapter 12, Statics. Questions that we'll answer in this video. What do civil engineers do? What types of loads can structures be subjected to? What is the difference between scalar and vector quantities? What does it mean if an object is in static equilibrium? And what are free body diagrams? Mechanics. The science of mechanics is the study of forces and their effects. Statics is the study of objects at rest, and dynamics is the study of objects in motion. Statics. When forces or force systems acting on an object are in a state of balance, the object is said to be at static equilibrium. Structure defined. A structure is a stable assembly of connected components that is designed to withstand loads. A truss is a triangular arrangement of members, commonly made of wood or steel, that forms a rigid framework. Structural members and loads. The strength of a structural member is defined as the maximum amount of force it can withstand before failing. Forces that are transmitted through a structural member called an internal member forces. The cross-section of a structural member is a very important factor in determining its strength. Cross-sectional area is the surface area of the cross-section of a member. Overview of forces. Newton's first law of motion states that a body at rest will stay at rest, and a body in motion will stay in motion in a straight line unless acted on by an external force. Newton's second law of motion states that force is equal to the mass of the product and the acceleration. So force equals mass times acceleration. Newton's third law of motion says that every action has an equal and opposite reaction. Forces have the capability of moving an object that is at rest, changing the velocity of an object that is already in motion, or deforming the object. Vector and scalar quantities. A scalar quantity has magnitude only. Vector quantities have magnitude, direction, and sense. The magnitude of a force is expressed in units, newtons. Direction is described as the path of the line along which a force acts. This is commonly referred to as the line of action. Sense is the direction in which the force acts along with the line of action. Sense is generally noted by drawing an arrowhead at the line of an action. Point of application is the location at which the force is applied to an object. Force systems. A force system is two or more forces that are collectively considered. All force systems fall under two broad categories: coplanar and non-coplanar. If all the lines of action of some forces within a system all lie within the same line, we refer to the system as coplanar force system. If the lines of action of some forces within a system do not lie in the same plane, then we refer to the system as a non-coplanar force system. Coplanar and non-coplanar systems can be further classified into concurrent force systems and non-concurrent force systems. Concurrent forces have lines of action that intersect at a common point. Non-concurrent forces have lines of action that do not share a common point. Types of force systems. Coplanar concurrent. The lines of action of all forces are acting in the same plane and pass through a common point. Coplanar non-concurrent. The lines of action of all forces are acting in the same plane but do not pass through a common point. Non-coplanar concurrent. The lines of action of all forces are not acting in the same plane but do pass through a common point. Non-coplanar non-concurrent. The lines of action of all forces are not acting in the same plane and do not pass through a common point. Vector addition. Two or more vectors may be added together to produce a resultant vector. There are different ways to add vectors. This is the tip-to-tail method. You can do this with two vectors. Step 1. Decide on a scale for your diagram and use a protractor and a ruler to draw forces F1 and F2 to scale. Step 2. Draw force F1 starting from the tip of F2. Step 3. Draw the resultant force and determine its magnitude and direction by measuring the length and angle of the line. Tip-to-tail method for three or more vectors. Step 1. Decide on a scale for your diagram. Step 2. Use a protractor and a ruler to draw each vector to scale. Draw the first force at the proper angle and the length starting at the origin. Draw each additional vector from the tip of the previous vector. The order in which you place the vectors is not important as long as you represent each of the forces once. Step 3. Draw the resultant force by connecting the origin to the tip of the last vector drawn. Measure the length and the angle of the resultant force to determine its magnitude and direction. Rigid bodies. An object that does not experience a change in shape or size when a force is applied to it is referred to as a rigid body. This is a theoretical concept because, in reality, all materials undergo some level of deformation when a force is applied to them. The principle of transmissibility. The principle of transmissibility applies only to rigid bodies. The line of action extends through the entire object, transmitting the force to the opposite side. External and internal forces. An external force is applied by a different body than the one being analyzed. A body or structure that applies a force to another part of the same body or structure is considered an internal force. Moments. A moment is a tendency of a force to twist or rotate an object. A moment is generated when a force acts on an object perpendicular to a moment arm distance, which originates at the fulcrum. The formula for calculating moment is force times distance. The unit is Newton meters. Conditions of equilibrium. The following two conditions must be satisfied for a body or a structure to exist in a state of static equilibrium. All forces must sum to zero. In two dimensions, we must consider both x and y components of these forces. Therefore, we can break down the sum of forces in the x direction and the sum of forces in the y direction. All the moments about any given point must sum to zero. Free body diagrams. A free body diagram is a simplified graphic representation of a rigid body, mechanism, or particle that is isolated from its surroundings and one which all applied forces are shown. Particle free body diagram. Drawing a free body diagram of a particle is very easy because all forces are concurrent and intersect at the same point. Rigid body free body diagram. Rigid body free body diagrams are usually more complex than particle free body diagrams because the forces no longer act on a single point. It is very important to label all known external forces. Simple supports and reactions. Simply supported beam that consists of one pin support and one roller support. These supports are commonly known as simple supports. A pin support allows a structure to rotate, but it does not allow linear movement. In the study of statics, we assume pin connections to be frictionless. Roller supports are able to rotate and move along the surface upon which the roller rests. A cantilever is a structural member with one built-in end and one unsupported end. One fixed support shows the supported object literally built into the supported surface. Simple beams. Step 1. Draw the free body diagram. Draw a free body diagram of the entire body being analyzed. The support reactions are represented by arrows with a diagonal line through each one. Step 2. Calculate support reactions. The magnitude and directions of the reaction forces that occur at the supports are calculated using the equations of equilibrium. Structural analysis of trusses. A truss is a structural system that distributes loads to supports through a series of members connected in a triangular pattern. Assumptions. In order to determine the magnitude and types of forces that are carried by the members of a truss, we must make the following assumptions. All members are perfectly straight. All members are pinned and frictionless. The weight of each member and the entire truss are neglected. All loads are applied to the joints, and no moments can occur within the truss. Static determinacy. The first step to analyzing a truss is to create a free body diagram of the entire truss. So here's an example. The formula to check for static determinacy is 2J equals M plus R. J is the number of joints, M is the number of members, and R is the number of support reactions. Setting standards. Measure all angles from horizontal so that we can always use F sine theta to solve for Y components and F cosine theta to solve for X components. When drawing a free body diagram, assume all internal member forces to be in tension. Step 1. Check for static determinacy. For example, there are 3 joints, 3 members, and 3 support reactions in the truss. So here we plug it into our equation. 2 times 3 equals 6. 3 times 3 equals 6. So 6 equals 6. This is statically determinate. So we can move on to the next step, calculating support reactions. Step 2. Use the correct equilibrium equation. So here's our different options. The sum of our moments, the sum of our forces in the x direction, and the sum of our forces in the y direction. Answer the following questions in your engineering notebook. Why is statics considered fundamental to all fields of engineering? When would one use a free body diagram? How do you determine the direction and magnitude of a reaction force that occurs at a beam or truss support location? And how do you determine the magnitude and type of force that is transmitted through a truss member?